Okay, so for today's lesson, we will be talking about thermal energy transfer in the atmosphere. So the three main types of energy transfer we're going to be talking about today. And I remember we talked about this already this year. I don't remember what unit it was in, but yeah, so this is three ways that energy is going to be transferred throughout Earth's atmosphere. So we'll start at the top left part of this diagram here. So the way that the sun heats the ground is through radiation. Okay, the sun emits electromagnetic radiation, so like ultraviolet rays, visible light rays, infrared waves, to name a few. Okay, radiation is like heating of a substance by the energy that it is contained in the waves of the radiation that is being emitted. Okay, shifting to the clouds now. So as warm air rises, this is considered convection. Okay, so if you open your back door or your front door during the winter, you might notice that a lot of the warm air is going to escape from your house through the top of the door as opposed to the bottom of the door. Remember, as air warms, it becomes less dense because it's going to spread apart, right? And as it becomes less dense, it's going to rise. Okay, so that is convection. And the ground that it is heating the air from direct contact, this is considered conduction. Okay. So big takeaways here. Maybe one way for you guys to remember this, which is really helpful for myself. So radiation. So for the three types of energy transfer we're talking about today, so radiation, convection, and conduction, this might be a helpful way for us to remember between the three, or help us just kind of learn it. So radiation, think of cooking food in your microwave. Okay, we use microwave radiation for that. Okay, and again, that is energy within the waves of the type of radiation that is being emitted. For convection, think of cooking food in your oven here. So convection ovens. I can't spell today. Food in your oven. There we go. Okay, and then conduction. Think of cooking food in a frying pan. Okay, so that energy is transferred through direct contact through conduction. Convection, it uses the warm air that is generated by electricity in your oven, and that warm air is going to rise. And then as the sun heats the ground from the, just admitting one more student. There we go. Okay. And then radiation would be like the energy that it is formed or that is possessed in the waves of that particular type of radiation. Okay. So a good way to remember these three is just kind of think of food, right? How do you cook your food? Is it radiation? Are you cooking it in the microwave? Are you cooking it in the oven, like baking it? That would be convection. Or if you're cooking in a frying pan, that would be conduction. Okay, this video here, this is the one, what if the sun disappeared? I'm not going to play it here, but I would expect you guys to watch this on your own. This is a really interesting video, actually. I really like it. So it's about 11 minutes long, so just take the time to watch that on your own, okay? Okay, so we kind of just talked about these types of energy transfers. Here's a diagram to, again, just kind of reinforce what we talked about. So three main types of energy transfer: radiation, conduction, and convection. So conduction, let's start with radiation. So here's just another image So convection is the warm air rising. Radiation will be the energy that is possessed within the waves of that type of radiation. And then conduction is the energy transfer from direct contact. Okay, so radiation, this is the transfer of thermal energy as waves. So not just infrared radiation. So we also have like ultraviolet, X-rays, gamma rays. Okay, these are all types of radiation. Think of the electromagnetic spectrum. Okay, so again, think of your microwave here. The transfer of thermal energy as waves. Okay, so put a big star, make sure you know what radiation is and how energy is transferred through radiation. Okay, and that is the transfer of the energy of the waves of that particular type of radiation. Okay, so like X-rays will have a higher frequency and higher energy than radio waves. So the second type of thermal energy transfer, so this is conduction, and this is the transfer of thermal energy by direct contact. So remember your frying pan analogy. This can occur between solids, liquids, and gases, okay? And again, that is the transfer of thermal energy by direct contact. And lastly, we have convection. So this is thermal energy that is transferred by the motion of matter. Hot material is less dense, so it rises. And this type of energy transfer usually occurs in fluids. You might be able to see this at home if you're like boiling a pot of water, right? You have conduction at the bottom where the pot is touching your oven. But as the energy is being transferred from the oven through the pot into the water, as those water molecules start to gain more energy, they're going to move further and further apart. And then eventually they're going to escape the atmospheric pressure and be released as steam, right? So just in general, hot things rise. Okay, so make sure you are able to describe the differences between convection, conduction, and radiation. Okay, so now that you know a little bit about convection, conduction, and radiation, we are going to talk about how energy is transferred throughout our atmosphere. Okay, so during convection, the movement of the particles will form a current. So remember, convection, this is like the movement of the movement of particles in response to thermal energy transfer. So is what happens. Remember, right at the equator, this is going to be the hottest part of Earth because it receives really direct sunlight, right? It has a low angle of incidence, especially if we compare it to regions at latitudes that are either more north or south of the equator. Okay, so it receives really direct sunlight, so it gets really hot there. And is what happens through convection, the warm ground will warm up the air molecules. And then as those air molecules are heated, they're going to rise. And as it rises, remember, we're going to want to go from an area of high concentration to an area of low concentration, right? So diffusion, heat would follow those principles of diffusion. So we have an area of high warm air concentration near the equator. So it rises and it kind of travels towards the North Pole. Okay, it's really cold at the North Pole and also at the South Pole. So once that warm air kind of gets to the North Pole, it's going to start to cool down and then it's going to sink. Okay, eventually that cool air will return to the equator again, where it will again be warmed and then it will rejoin this cycle. Okay, we call these circulation cells. And this is just kind of the general pattern how wind behaves on Earth. Okay, this is responsible for the continuous air movement on Earth, right? So cool air comes to the equator, it gets warmed, it goes back up to the North Pole, and then it cools again and returns to the equator. So the Coriolis effect, this is the deflection of an object because of its rotation. Okay, so I don't know if any of you guys have ever been on a merry-go-round, right? That's the thing that you jump on and it spins and it spins and it spins. If you were to try to roll a ball off of the end of a spinning merry-go-round, it's going to be influenced because of the direction of the merry-go-round. So if we pretend that Earth is a really large merry-go-round and it's spinning, as that air, the air that is returning to the equator as it's cooling, as that air is returning to the equator, because the Earth rotates from east to west. So it goes in this direction, right? So kind of, it rotates from east to west, right? So the eastern part of Canada will see the sunrise first, right? So if the sun is over here, as that Earth rotates this way, it will see the sun first. And that is why the west coast of Canada will see the sunset last, right? Because the sun is here. Remember, Earth orbits the sun. So as the Earth rotates, the eastern part of Canada gets the sun first. Now, eastern part of Canada will be right here. It's starting to get dark, and then sunset is in Western Canada. I hope that was a good model for the rotation of the Earth. Okay, but anyways, as the Earth rotates, as the wind or the air is returning to the equator, that wind is going to be kind of pushed towards the west, just because of the rotation of the Earth. Okay, so that is what occurs in the northern hemisphere, and it's actually just the opposite in the southern hemisphere. So it is also going to go to the west, but if we were looking at it from top down, from the northern hemisphere, it's going to shift to the right. And if we're in the southern hemisphere, it's going to shift to the left. In both cases, it's shifting to the west, opposing the rotation of Earth. Okay, so just to summarize, as Earth rotates, the effect makes winds in the northern hemisphere turn in the opposite direction than in the southern hemisphere. Okay, and again, there is a wicked video on the Coriolis effect at the end of this presentation, and I've included that link to the Google Classroom, so check that out today, please. Okay, so global wind patterns. In general, the Earth does have some prevailing winds. And again, this is just caused by the Coriolis effect, so the spinning of Earth affecting those winds as they return to the equator. And yeah, so the Coriolis effect and the convection of that air is responsible for causing the global wind patterns. And we already talked about this. Cool air sinking from the poles will cause winds to blow mainly from the east. Okay, because we are so close to the west coast, we generally have a westward blowing wind. But if we were closer to like Montreal and PEI, we would experience quite the opposite, where it'd be more of an eastern wind. Jet streams are high-speed winds at very high altitudes. Okay, you may have heard of these jet streams. This is how weather, one way that weather can kind of like travel so quickly across our Earth. Okay, so this image is just kind of showing just like general jet streams, and also talks about the currents of the ocean. Okay, so we have the Gulf Stream. We'll have some warm currents, so we'll notice that we'll have some like circulatory effects over here. Notice in these particular regions where we have like circulatory currents, we do actually experience large collections of trash here. In particular, in the Pacific Ocean, they have large amounts of trash in there. It's the actual area itself is called the Great Pacific Garbage Patch. I don't know if you guys are familiar with that or if you've heard that before. Okay. Those Great Pacific garbage patches are caused, well, one, because a lot of the trash gets dumped into the ocean, and two, because of these circular ocean current streams, it just kind of like naturally collects the garbage, which when you think about it, it's like, well, if it's all collected in one nice, neat area, shouldn't we just go and clean it up? I think we should. But apparently it's so big that it would take a lot of time and energy and resources. And if we are still dumping our trash into the ocean, it is almost seemingly inevitable that it will still return to that particular location. Okay, so you don't need to know this map at all. I just wanted to show it to you, just to kind of show what is going on a global scale for kind of wind and ocean patterns. Okay, this last thing here is a video on the Coriolis effect, so please take the time to watch that, which we will not watch. And that is everything for today, for today's lesson.